let me recall. In fact, we reached, in some sense, our final destination, and we will work with this almost until the end of these lectures. And what is this? Let's recall what we did last time. So let G be, let's say, we have field of complex numbers. It can be relaxed sometimes, but in order to avoid some difficulties, we only work for complex numbers. Let G be semi-simple Lie algebra. Okay, finite dimensional. And what we did the following. Starting with semi-simple Lie algebra, we can choose some Cartan subalgebra. Cartan subalgebra, it's like maximal toric subalgebra. We will prove it in some points that every Cartan subalgebra, in fact, is just maximal toric subalgebra. But now, let's recall what is Cartan subalgebra. It's a subalgebra consisting of semi-simple elements such that it coincides with its centralizer. Yeah, there's another definition which works for every the algebra, not only for semi-simple. It also coincides with normalizer, but then it is nilpotent, maximal nilpotently subalgebra, which coincides with its normalizer. Now it's maximal abelian subalgebra consisting of semi-simple elements, which coincides with its centralizer. So it's different definitions. But anyway, we know that we have some, because we proved that any maximal toric subalgebra is Cartan subalgebra. So, and we constructed the following data. We constructed Euclidean vector space, and root system inside it. System. And it turns out that this is bijection. But in order to prove it, we need a lot of work. It's not very simple. We only did some simple part, which is already non-simple, but like we constructed this, and now we should prove that this is in fact bijection. And there's a lot of work. So first of all, why it is correct? Why it is? We still don't prove that it is map. Because first of all, we should prove that it is map. And then we should prove that it's surjective and injective. Yeah, and this is moreover, yeah, and that's true. And moreover, we can classify these objects, and this is simple. We will do it maybe next time. We will start on seminars today. This is simple part because it's just some finite subset of vector space, of Euclidean vector space with simple properties, and yeah, therefore we can prove that this is bijection and classify all these guys, and then we will obtain classification of all semi-simple, and it's enough to consider simple of all simple Lie algebras, because any semi-simple is sum of simple ones. But here is a lot of work. Moreover, we already used some facts which we didn't prove. And today we want to discuss this. First of all, maybe it's not the simplest way to prove what we already used. Which fact we used which we didn't prove? When we are doing this, we use some fact which we didn't prove. Which one? We didn't use Otto's theorems for this. But we didn't use it for anything. We use it only for some problems probably, but like for exercises. But we didn't use Otto's theorem is not necessary for our purposes, like, because we are only interested in semi-simple algebra. They are already like Otto's theorem for semi-simple is obvious, but yeah, no, we didn't use it really. For this we didn't use. But we use something for this, which we what we used. No, we did. No, it's part of this. To prove that this is map, we should prove that it doesn't depend on Cartan subalgebra. Otherwise, if it depends, then it is not map. No, we used. But what is the key point? How we constructed? What is the key point? Why root system? Maybe I need to let's recall the definition of root system. Root system is a finite subset phi of E of non-zero vectors, where E Euclidean space I already wrote, such that first phi spans E, secondly if k alpha phi, therefore, and alpha belongs to phi and k alpha belongs to phi, k is equal to plus minus 1. In fact, like this. To alpha beta, where alpha belongs to Z for any alpha betas from phi, and the last that S alpha of phi, subset of phi, where alpha for any alpha is from phi, and S alpha is just reflection with respect to hyperplane perpendicular to alpha. Okay. Yeah. So, and now we're starting from some objects, simple algebra, and now we finish just with like very symmetric configuration of vectors in Euclidean space. For example, in two-dimensional space, you could consider, we already do it on previous seminar, that we have such a root system. Here's pi over 3, and this is called A2, corresponding to the algebra SL3. Yeah, we restricted our killing form to the IH is non-degenerate. Then we consider some all Q linear span of these guys. It turns out that their dot product is always not dot product. Is a killing form on them. It's always rational. Then we and moreover positive defined. And then we consider extension of scalars extended to R and get Euclidean space. So this is A2 corresponding to SL3, but we will consider more examples, and you had some on your homework today, and we will continue today because it's important to know the list is not very big, and it is possible to know almost all these guys, and it is necessary sometimes. Okay, but okay, which statement we used without proof? No. So we proved this, everything. Some of this was the most, the simplest was the longest. But anyway, what is the idea? In fact, it's a consequence of the consequence is the representation theory of the Lie algebra SL2C. All of these properties follows from the fact that in any, let's recall that how we do it. We have this decomposition, which is called root decomposition. And if all these spaces are one-dimensional, And if you consider x alpha, x minus alpha, and their commutator, then this is isomorphic to SL2C. So for any root, you have the corresponding SL2C subalgebra in your semi-simple algebra. And we used the representation theory of SL2C, which is very restrictive, like classification of representation of SL2C. And in fact, all these properties are consequences of this, that this Lie algebra itself is representation of this guy. So using this, we obtain all these properties. So it's not very surprising. Okay, but we used the fact that all representations of SL2C are completely reducible. And their classification. Their classification is in fact very simple fact. You could find the classification in lecture notes of reducible. Moreover, there is the proof, some like by hand proof that the representation of concrete algebra SL2C are completely reducible. There is some proof, very concrete. It's useful in some cases, but in fact, anyway, we will study. So the main goal of this course to study classification. So it's for next month or two, and then study representation theory. Anyway, we will study representation theory of the semi-simple algebras, which is also very, very interesting, and in some sense very simple. Therefore, we want to prove today that every representation of semi-simple algebra is completely reducible. Okay, theorem. For any semi-simple, we will prove it, not for SL2, for any. Yes, it's simple fact, but we will not the idea. Yes, but but it's already. But we will see. Maybe we'll have some time after this. Then every representation. Formally, it's possible to prove it very fast, in 20 minutes, but we want to do it. Every finite dimensional representation of semi-simple algebra, Lie algebra is completely reducible. It means that every representation is direct sum of irreducible representations in a unique way. Yes. Finite dimensional. Finite dimensional. We don't have this chunk. No. For sure, there are some infinite dimensional representations. It's only for if you yes. If you're interested in all representations, then there is Krull-Schmidt theorem, which said that every representation of Lie algebra is direct sum of indecomposable representation in a unique way. Because if you consider some Fermat model for SL2, it could be not reducible, but it is indecomposable infinite dimensional representation. So like it's for finite dimensional algebra, there is always a theorem. If you have finite dimensional algebra, then every representation is the direct sum of indecomposable representations in a unique way. It's called Krull-Schmidt theorem. If your algebra is not finite dimensional, that is not necessarily true again. And in fact, it's in more general setting, it's theorem for modules over rings, over arbitrary ring. It is not true, but if your module is Noetherian and Artinian at the same time, then it's true. Any other questions? Okay, let's prove this. In order to prove this, we will use Lie algebra cohomologies. We will use first we will not define all Lie algebra cohomologies, but we will use first cohomologies. In fact, we need okay, proposition. So idea using H1 V idea where V is any finite dimensional representation. It turns out that this theorem follows from the fact that for any fact, it's called Whitehead's lemma. I don't remember how correctly write his surname. Therefore, for semi-simple Lie algebra and finite dimensional representation, H1 is equal to 0. In fact, it's the same as extend, so probably it's parallel to prove that what we need to prove, that any extension of representation is split. It's the same to prove that X VW is 0 for any pair of representation, and follows from this. We use this. But we need to define what is this, right? So let's define. Definition. Let's define. Yeah, maybe how. Whitehead's lemma. In fact, there are two lemmas. H1 is equal to 0, and H2 also is equal to 0. And H3 is not. What are the algebras cohomologies? If you know some cohomology theory of manifolds, probably you know the RAM cohomologies. And you know that Lie algebra is ordinarily not just Lie algebra, it's Lie algebra of some group. And group is manifold, right? And this group has its own cohomologies, the RAM cohomologies. And this is like counterpart of the RAM cohomologies. In fact, there, in some good cases, this is equal to the RAM cohomologies of the corresponding group. So, like you have cohomology theory for topological spaces, for manifolds, right? And you have its counterpart in linear algebra. So they correspond to the RAM cohomologies. In the RAM cohomologies, yeah. If in the case if it's some field, yeah, this is the same as the RAM cohomologies. Yeah, if V is K, if V is not K, then yeah. If V is K, yeah. But in fact, in this linear algebra setting, it can be extended to any module. But in fact, you can consider cohomologies. Okay, maybe. Okay, so let's consider the following vector space of maps from G to V, such that f of AB. Okay, now you see why we will spend the entire lecture to prove this theorem, because we need to introduce a lot of things. A f of B minus B f of A. This is obviously some vector space, and it is called the space of one cocycles. Yeah. So for completeness, I should define complex, which corresponds to Lie algebras, and differential, yeah, and its cohomologies, and it's possible to do it. But we only need first homologies, so I just define them by hands. So this is called one cocycles with values in V. We can consider so we can consider how it's called. Okay, let's call it trivial one cocycles, which corresponds to Fv, where Fv of A is equal to Av. So I claim that for any for any vector in representation, this guy is one cocycle. This is called trivial one cocycle. Or how it's co-boundary, one co-boundary. F is any linear map with this property, linear. When we work with vector space, all maps are linear. Let's check. What does it? Let's check this property. I claim that this B1 is inside its subgroup or subspace. It's a subspace of this, right? What I need to check? I need to check that. Check that Fv of AB is equal to A. What is A FVB, right? Minus B FVA. But it is just definition of representation, right? So because this is ABV, this is BAV, and this is FAB on V. Here you have, right? By definition. Here you have, and here you have. This is equal to this because it is representation. It is representation. Okay? Yeah. It's A dot V, so we have representation. V is representation. Yeah. So let's. V is representation. A is its action of A on V. I could use row of A on V, but then this could be. Okay, so this map is always one cocycle. Therefore, we can define one cohomologous as H1 of GV is equal to Z over B1 of GV. Okay. And we need, yeah, okay, we still don't need this. And moreover, what is interesting that I claim that we can easily deduce from this this theorem. This is called Weil theorem. Weil theorem. Weil complete reducibility theorem, and he proved it in completely different way. And there is another theorem which connected with this. There is Levy's theorem. We will not have enough time to do it, but I will put it on the page. So in fact, Levy's theorem about, let's recall, decomposition of any Lie algebra into semi-direct product, semi-direct sum of semi-simple and radical, it also follows from this lemma. So therefore, it's pretty interesting property. Okay. Now, so we need some. So our purpose is to prove that the first homologies are zero. But first of all, yeah, if you have direct sum, then probably the following is true. These are all vector spaces. Is it obvious? But it's enough to prove that this is direct sum and this is direct sum, right? Is it true that one cocycles, if you have direct product or direct sum of two representations, then so proof. Okay, Z1 of G v1 plus v2. What is this? It is just some map from G to direct sum with the following property. Can you, so let's prove that it is okay, we have two guys and this. Maybe some inclusion is obvious. It's just sum of this and this. So this is obvious, this is obvious, this is just sum, right? Because it's by components, it's obvious. But if you have this map, you could consider projection, composition with projection, right? You could consider, if you have here F, you could map it to F composition P1, F composition with P2. Moreover, it's obvious that this maps are inverse to each other. So this is indeed isomorphism. And what about this? This is just concrete maps. Again, if you have, so now you have FV, you decompose into some two vectors, v1 plus v2, and consider map which maps this. Okay, it's okay. Let me say this is obvious. This is also direct sum. Therefore, we get this. Okay, this is obvious. Okay. Now we need Casimir element. Let's define it. Let me ask you, do you know what is a universal envelope in algebra? Nobody knows. Okay, then we will not use this to define. Huh? Do you know what is universal envelope in algebra? Универсальная обертывающая алгебра. You know? Don't know? So, okay, we will. In fact, so in order to define Casimir element in good way, we need universal envelope in algebra, but in bad way, we can do the following. Okay, definition proposition. Let G be semi-simple and xi be a basis of G and xi be a dual basis with respect to Killing form. Okay. So we have semi-simple algebra, we have Killing form, it is not degenerate, we can choose any basis, we can choose dual basis. What does it mean, dual? Dual basis with respect to Killing form. And consider the following element. Consider element omega, which is equal to sum I from 1 to dimension of G xi times xi, and it doesn't make sense because I can't multiply elements of Lie algebra. If you know what is universal envelope in algebra, then you could consider this as element of universal envelope in algebra. If not, but anyway, this guy acts on any representation. So in other words, so in U of G or for if V is representation rho V, then omega rho is just sum to dimension of G, rho of xi, rho of xi. Okay, and this is well defined. This composition. So then it will be Casimir element in this representation. Is Casimir element and this is just Casimir element. You can ask in Russian. Because if you have representation, any element of the algebra act by something. What is the question? Why we have dual basis? Because form is non-degenerate. If form is non-degenerate, you can always find dual basis. Yeah. Is also basis of Euler algebra. Yeah, it's obvious. It's another basis. No, it's in G. So as you have non-degenerate form, you can identify G and G star, therefore, by means of this form, and then dual basis is what corresponding to dual basis in this sense, under this identification. You could define it like this, but yeah, it's exactly what you said. Huh? Omega in one, so if like universally it's element of universal and open algebra. If you don't know what is a universal and open algebra, it's not really necessary. You consider any representation and consider such element in the representation. And this is Casimir element for this representation. First of all, in this definition, I wrote that it's a definition proposition. Why? What is not obvious? Let's say the if you know English, then now there is some statement. Like it is a unique element. I wrote the Casimir element. It's unique, but in order to define it, I use some basis. If I choose another basis, probably it could be different element of universal and open algebra, or so this belongs to endomorphisms of V. It could be different linear operator. In fact, it is not different. Let's prove it. There are different ways. In order to give a clever proof, we need to know what is universal in open algebra. But if we don't know this, we can just do it by hands. Let's do it by hands. And then I will say some words about why it's obvious. If you study linear algebra with Alexei Gorodentsov, you should know this. Because why it is unique. Okay, how to prove that it doesn't depend on basis? Any ideas? That's in some senses obvious. It's possible, but we don't like to compute a lot how to simplify. If you have any linear map, can you decompose it in some simple linear maps? Do you know so-called Gauss method? Well, unfortunately, it's like everything. What is said is that any linear map can be presented as composition of three types. First type is what? You multiply vector by some number. You change AI to lambda AI, right? A second type, we start with basis, with some basis. okay, and we want to map it to basis of E1, En of our, for example. Then secondly, we can exchange, right? We can AI to AJ, AJ to AI. And third, we can add to basis vector some other basis vector multiplied by some number. So AI to AI plus lambda AJ. I is not equal to j, lambda is not equal to 0. Right? And Gaussian method said that any linear map can be constructed as composition of these three. You can compose this. It's like with any non-degenerate matrix, you could get just matrix with identities using this Gaussian method. Okay, and how basis is changed under this? So our element is defined using dual basis. If we do this kind of transformation, how we change our basis? Dual basis. For example, B1, Bn is dual. So this corresponds to what? What happens with dual basis? Right? And then nothing changes. You get the same, right? What happens here? No, it's just permutation again, right? And for last, the most, how dual basis is changed under this. I mean, all others are the same, but okay, and here it's also obvious that omega is the same, right? You just exchange. Dual basis corresponds to dual matrix, which is transposed matrix. Do you know that if you have linear map, then you have dual map from linear functions to linear functions? I mean, it's in some sense obvious, but no, this is no. You can think that your matrix of Killing form is 1, 1, 1, 1, 1, if you want. You have only one non-degenerate complex by linear form. Okay, let me write and let's check just. I claim that it's obvious that it is this. Okay. Why? Is it all? So let's check. So what I need to check? I claim that this basis is dual to your original basis, right? So I have to check that if you have AI prime. So what I need to check? First of all, I need to check that AK BI is equal to 0 if k is not equal to I. because others not changed. Is this true? Because our bi, okay, let's say bi prime. So ak bi prime, it should be 0. Is it 0? It is 0, so that's okay. Yeah, so let's check. So is it is 0 when what? When what? If I is not equal to k, is or if what is, if j is not equal to k, then it is 0, right? So let's check so that we have new basis. Okay, we have a1 prime, an prime, and b1 prime, bn prime. So now I have to check that ai prime bj prime is delta ij, right? So I have to check that ai prime bj prime is equal to 0 for any I is not equal to j. So what I have, if you have ai prime, if ai prime, let's say that I is not equal to so the only question is what we get if you have ai with what? For example, okay, let's compute ai bi prime, ai prime bi prime. So here you have ai minus plus lambda aj, here you have bi minus lambda bj. What do you get? So it is equal to ai plus lambda aj, you have bi minus lambda bj. Then what you get here? Here you get ai bi, it is 1 plus, so these are zeros, and this is plus lambda, 1 plus lambda squared, right? Minus lambda squared, okay? Yeah, I should change I and j, right? Okay. So bj prime is, because we transpose, yeah. Yeah. Okay. Yeah. So then, so let's compute ai bj prime, right? Then you will have ai plus lambda aj, and here you have bj minus lambda bi. And it's indeed 1, just 1. Because these are 0, this is 0. It is 0, right? Well, because zeros and cross terms cancelled. But for all others it's the same. Yeah, they cannot coincide. They can't coincide. That's y4. ai prime is ai plus lambda aj, so this is our change. Then bj prime is bj minus lambda bi. I just compute concrete. So it's not arbitrary, but for all others it's obvious because nothing changed. So the only non-trivial is this guy, and we computed it. All others is trivial. Okay, so okay, and what happens if you do this substitution into your Casimir element? Let's check. So you could compute in this form probably without letter rho. It's the same. Then here what is changed, only you have what's changed, you have xi plus lambda xj x I as before, right? It's obvious. What is question? This is obvious. You could compute. Is 0. It's not the same. It's not orthogonal map. All others are the same. We only change only one. Yeah, I said it like, but probably. Yeah. Okay, what's changed? It's here, right? All others are the same. Plus xi times, okay, this, right? X j plus lambda, x j minus lambda x I. And we see that the cross terms cancelled. So our element does not depend on choose of basis. Clever way to think about it is the following. Let's consider G cross G star. Probably you know that it's isomorphic to endomorphism of G. And this is the same as G of G, G times G. And here you have identity element. And it corresponds to omega under this map. If you recall how this map is working, then this Casimir element corresponds to identity map of this endomorphism. Therefore, it doesn't depend on change of basis. So this is clear ways to think about it. But like, we need notion of universal and open algebra. So we have inclusion of the universal and open. Not inclusion, but map. Okay. Now, so Casimir element is the main tool to prove it now. Okay, so we have Casimir element. Okay. So now I need the following lemma. So let's suppose that oh, here it was another letters, but okay. Which letters I use? Xi and Xi. Oh, that's bad. Okay. Okay, AXI is just sum of AIJ, AJ, commutator. Let's write commutator of some element. Let's A be from G, and we'll write commutator of A with basis element. And we can write commutator with dual basis element. XG. And we can write with dual basis. It is like Bij xj. Then Aij is equal to minus Bij. So commutator on basis and dual basis, the corresponding coefficients are just like inverse, additive inverse. Okay. So proof. AAI, consider AAI and consider its product with B, AXI, and consider its product with XJ. And this is equal to what? AIJ. First of all, it is equal to AIJ, obviously, by definition of dual basis. Moreover, it's invariant by linear form, so it's equal to so it's equal to AXI and XJ, and moreover, it's equal to minus, right? Minus A, AJ minus A. Okay, so let's see what we want. And we can play the same game with AXI. AXI XJ is equal to what? BIJ. Yeah, we consider commutator here and pair it with XJ. We get BIJ. Okay. And now our form is invariant, and I want to say that this is equal to minus this. Is this true? So okay, let's see. So if you could write this is equal to A xi xj, right? And you could write because sorry indeed it would be bji, so xj xi. Okay, probably now it's better, right? Now it is a xj xi, and this is equal to a xi xj, so it's indeed equal. Okay, so aij is equal to minus bji, and now no, here it's not minus, here's just bji. Okay, let's write it like this. It follows. You do not need here minus anywhere, so okay? No, no, without minus. Okay. Now let's prove the following. So we need to do one computation. Huh? Why it is what? Because this is equal to minus this. Just because here you have xj xi, here is xi xj. So now proposition. So it's a big computation, the main big computation in all this stuff. I claim the following, that for any A from G, we have the following formula: A act on AI for and F be one cocycle. Then I claim that A times xi f of xi is equal to omega f of A. So let's understand what is written. So omega is just some linear operator, f is one cocycle, so this is an element of representation, then you act by omega. And it is the same as you consider this thing. It's like you apply your cocycle to second coordinate of omega, f of xi. Now it's an element of your representation. Then you act by some element of the algebra, again element of representation. Consider this sum and act by element A. So it's like omega where I apply f to second factor of omega. So this is a big computation. In order to let me first skip it and continue. So this is, but what is follows from this corollary, and just computation. You should use this. So like you write it in basis and compute and get this. For example, if f is one coboundary, what you get here? What follows from this? So for one boundary, this, let's recall that, so f is equal to f v, so, right? So we will prove it, but later. Like, first of all, I want to show why it is important. And so this is the main computation of this. Everything, every other things is not. This is just some computation. But let's apply it for one boundary. So f is fv. Then what you have here? It's written that a sum of xi, f of xi is what? Is xi v, right? So in other words, this is just a omega of v, right? Is equal to what? To omega of av. So in other words, it said that omega is morphism of representation. Therefore, omega is morphism of v. So this Casimir element is always morphism of representation. If your representation is reducible, it is always acts by scalar. Okay. Or in terms of universal envelope in algebra, it's element of center of universal envelope in algebra. So it's like universal morphism of representation. It's always morphism of representation. So this makes sense. And suppose that we have this, and let's see how we can prove, and then we will go back to this computation. So we want to prove that h1 is equal to 0. Okay. Proof of Whitehead lemma. So consider omega. So we have representation v. Consider omega rho. Omega rho commutes with action of representation. Then you have if you have some element which commutes with action of v, but it's some linear operator, right? You could consider decomposition of v into some of its generalized eigenspaces, like it's b0 plus just like some lambda is not equal to 0 v lambda. So v lambda is just kernel of omega rho minus lambda e power. So it's generalized eigenspace decomposition. What you can say about these subspaces? They are invariant. So they are some representations. So all v0 and v lambda are sub-representations of v. What is p? V. Omega rho. Rho v. Okay. Yes, it's morphism of representation and it commutes. So if you read in lecture notes, the proof that for SL2C also used this as well. Okay, now this also representation. You want to show that h1 of GV is 0, but h1 of GV it's h1 of GV0 plus direct sum of is non-zero h1 of GV lambda. Okay. So it's enough to prove that all these guys are zeros. So we decompose our representation into sum of generalized eigenspaces for Casimir element. Okay. First of all, consider h1 h1 of gv0. What I can say? I can say that let g0 be the kernel of rho, kernel of representation. So this is some ideal in G, right? Okay, this is ideal in G. Therefore, semi-simple. Any ideal semi-simple algebra is semi-simple. Therefore, G0 is equal to its own commutator. Right. Very good. If you have f1 cocycle, then what we have that f of AB. Let's recall that we want to prove that we still have definition, right? A f of B minus B f of A. Because rho is homomorphism of Lie algebras. Because rho is homomorphism of Lie algebras. The kernel of homomorphism of Lie algebras is ideal. Okay. Okay. Very good. So now we consider V0 subrepresentation. Then what we know about, so we consider one cocycle and what we know about action of our Lie algebra on it. If you have AB from G0, then it is what? It is 0, right? Because it's act by 0. It is 0. Right? Therefore, f of G0 is 0. Therefore, f of G0 is 0. So, in other words, any one cocycle is 0 on G0. Right? Any one cocycle is 0. So, if we have representation, consider its kernel. Consider one cocycle of this representation. Then this one values of one cocycle on this on kernel is 0. It's in fact it's for any representation. It's near here. It's still not important that V0. You can think that V here, yeah. But it means that you can it's you have well-defined map from G over G0 to V, right? And it is also one cocycle. Okay. So it's well-defined map. If we want to prove that H1 first cohomologies are 0, so we do not. If we want to prove that first cohomology is 0, it's enough to consider. So I claim. So let's denote it by G bar. It's enough to work with G bar. Let's write it. Because it's one cocycle, it's equal to this. And this map acts by 0 because it's kernel of representation. So we just say that any one cocycle can be, how it's called? Okay, we can get a well-defined map from the factor to V. It's enough to prove. that h1 of g bar v is 0. Why? So I just want to say that if you want to prove that h1 of gv is 0 for any finite-dimensional representation, it's enough to prove for g bar, for this factor. Why? Okay, because if you have one cocycle here, you can obtain one cocycle here, you obtain one cocycle on g bar. If you have one cocycle on g bar, you obtain one cocycle here. It's equivalent things. But it's still about, it's not about direct sum, it's just for any representation. It's not about direct sum, it's for... It's just, it's different statement. We can reduce our to, it's enough to prove for g bar. It's not about this decomposition. And now we can think that g is equal to g bar and use decomposition. Нет. Why? And okay, and what? Okay. So it's enough to prove to that h1 g bar v is equal to 0. And now, okay, consider. So now we think that g is equal to g bar. So g is equal to g bar. So we have exact representation. So rho is exact. Okay. So consider the following form. We have g rho v is exact. Consider form on G. Okay, trace form corresponding to this representation. What we can say about this trace form? I claim that it is non-degenerate. Why? Suppose that it is degenerate, then its kernel is so suppose that it is non-degenerate. J is not relaxed, J is semi-simple. G is semi-simple. Suppose that this form is degenerate. So we have some kernel. Kernel is ideal. Suppose that degenerate, then kernel is an ideal where in row of G. Right? And representation is exact, then it's some ideal in G, and therefore there is an ideal in G. If G is simple, then what? Is 0, because or everything, but it can't be everything. So then if it's semi-simple, it's also 0 or everything, because it's intersection with each component. Because simple algebra do not have. If it's simple, then semi-simple is direct sum of simple. For any simple, it is semi-simple. What is question? What is your question? Suppose that if your Lie algebra is simple, this is 0. Semi-simple is direct sum of simple ones. Then it is 0 for semi-simple as well. Because you have inclusion of your because your representation is exact. Okay. So okay. No. What we can say. So consider trace on V0. So let's recall that we have this decomposition. Consider trace on V0 of what? Of this Casimir element omega. It is equal to what? So it is just trace of V0 of xi, right? Of xi, let's say xi, so without rho for simplicity. And it is just what? It is just trace on V0 of xi, and this is equal to what? To dimension of G, right? So it's 1, 1, 1, 1, 1. Okay? Casimir element, right? So here we go. Okay. Better. What is xi and xi? It is 1. It is not trace. So here it's not trace, it's just how it's called. Killing form. This? So here it's for V0. First, second. But it's by definition, so it's our form. Our form. We have faithful representation, so our Lie algebra is subalgebra of GLV. So what's okay, but what we can say about omega on V0? If you compute omega on V0, so it is equal to what? To 0. Because V0 is just I mean, so omega of V0 is nilpotent. Therefore, trace of omega on V0 is 0. Therefore, G is 0. That's bad. So dimension is equal to 0. So we have proved that therefore H1 of, so it follows that H1 of GV0 is 0. If for, so we have this lemma, so let's consider H1 of G V lambda. Lambda is not equal to 0. Consider one cocycle f from G to V lambda. Then we know the following property for one cocycle, right? We know that A over, yeah, for any one cocycle we have A, so let's write it like this: A some element M is equal to omega f of a, where m is, okay, this guy, m is sum of xi f of xi. Okay, but what we can say about omega on this space? It's invertible because we do not have any zero. Omega is invertible. Omega is invertible. So we can write it as that f of a is equal to omega minus 1 am. Right? So, but it commutes. If omega commutes with a, omega minus 1 is also commutes with a. So it's equal to a omega minus 1 m. It's for any a from G. Okay. Therefore, we see that f is equal f omega minus 1 a omega minus 1. So we started with arbitrary one cocycle and get that it looks like this, right? It's one coboundary. The homologies are 0. So. In fact, it's not necessary to consider any, so it's enough to consider direct. We could consider direct sum at the same time. It's not important. Okay, so therefore we have proved that homologies are 0. Any questions? M where? Yeah. Thank you. It should be vector, right? It should be vector, which is equal to what? Sorry. Yeah, sorry. So like this. So I was not right. We not able to prove it in lecture. Okay, let's have a break and then we will prove complete irreducibility theorem after it, and then